Welcome back, friends. We are in model number 2, second part. As I have introduced alluvial channel carrying sediment laden water, and we discuss Kennedy's theory. But today we are going to discuss about the Lacey's design theory, which is also applicable for that particular conditions. So Lacey was the chief engineer in UP Irrigation Department. On the basis of his study, he observed certain drawbacks in Kennedy's theory. Since, as we discussed, Kennedy's consider only the eddy generation from beds itself, and he neglect the eddy generated from side. But Lacey observed that drawbacks in Kennedy's theory, and he developed his own theory for design of alluvial canals. So he defined a regime conditions, 3 regime conditions, as we see in a slide, that initial regime condition, true regime condition, and final regime condition. So as I have mentioned, if the bed slope is vary and weighted perimeter remains unaffected, but then the condition of non-silting and non-scoring may exist, which is called initial regime conditions. But the Lacey's define this condition, but this theory is not applicable. His theory is not applicable for such a condition. Then he designed a true regime condition. What does the true regime condition mean? It is an artificial one which has fixed slope, discharge, and uniform rate and fixed amount of silt, means concentration of silt is uniform. But this is the ideal condition. Such a condition is not exist in reality. But the Lacey's design theory is based on this condition itself. He gave some formulas, as we discussed in a short while, and he defined the final regime also, in which he defined the final regime conditions such a way that the variables such as perimeter, depth of the flow, those parameters are free to vary and can adjust according to the discharge and silt rate. For this particular condition, there is neither silting and non-scoring occur. Such a channel is said to have achieved a final permanent stability. If you see our alluvial channel, which is in permanent stability conditions, and this condition is known as a final regime condition, and Lacey's theory is valid for these types of channel. Based on this particular regime condition, he developed some empirical formulas to design a canal. Based on the regime theory, Lacey gave his own formula for the design of alluvial channel. As we see, the silt factor F is equal to 1.76. The design parameter which required in this particular type of design of canal is the discharge, means the flow in meter cube per second, and second one is the silt particle size in mm, or if available the angle of internal friction or repose angle. That's all. Then he gave formula for silt factor, F is equal to 1.76 root of D. Then he gave for perimeter also, P is equal to 4.76 root Q is in meter per second, Q is in meter cube per second, and P is in meter. And he also defined the velocity, V is equal to 10.8 into R to the power 2/3 S raised to the power 1/3. Many state level exam, they will ask this formula. Then R is equal to hydraulic mean depth is equal to 0.48 in bracket Q by F1 raised to the power 1/3. and he also gave the its own formula for longitudinal slope calculation. That is S is equal to f raised to the 5 by 3 upon 3340 to q raised to the power 1 by 6. So design step. What does the data required for the design? Data is required is design discharge in meter cube per second and size of the silt in mm and side slope if it is given, and Lacey also gave us side slope that one vertical to half horizontal. So in second step we calculate the velocity as v is equal to q f square divided by 140 raised to the power 1 by 6. If we q put in meter cube per second, then we will get velocity in meter per second, and f is the silt factor to calculate 1.76 root of d. Then in third step we calculate the hydraulic mean depth, that is r is equal to 2.5 v square by f. V is in meter per second and f has no units, then hydraulic mean depth will get in meters. So in fourth step we calculate p is equal to 4.75 root of q is in meter cube per second, then we will get the value of weighted perimeter in meter. And fifth step we calculate the area of cross section trapezoidal section, as Lacey suggested that provide the whatever the discharge is, but must provide the trapezoid section. So q is equal to discharge upon velocity as per continuity equation. Then in sixth step we calculate the b and y, that is bed width and flow depth. How do we calculate? As we have side slope, based on side slope we calculate the geometric parameter, that is area is equal to half of parallel side means b plus top width divided by 2 into y, and weighted parameter p is equal to b plus twice y root of 1 plus z square, means that length of the sloping side. Then we have p value and a value of the perimeter and value of the area. Then we put in these two equation and solve for b and y, we will get the b and y value. So in seventh step we calculate the longitudinal slope, that is s is equal to f raised to the power 5 by 3 upon 3340 q raised to the power 1 by 6. Then in final step we write down the design solution. As design what is our design solution? Our design solution is bed width, flow depth, longitudinal slope for a particular discharge.